Go outside on a clear night away from city lights. Look up. Thousands of stars. Some bright, some barely perceptible. The Milky Way, if it is dark enough, a band of hundreds of millions of stars merged into a hazy glow. In almost any direction you look, there is probably at least one star. And yet the sky is black, not slightly dark, not grey, absolutely black between the stars. A darkness that seems total and complete, even though the universe is literally filled with sources of light. Why? This is a question astronomers have asked themselves for centuries, and it seems simple, almost childlike, until you start thinking about it seriously. Because if you think about it deeply enough, it leads not just to an answer about the sky, it leads to one of the most fundamental facts about the universe, about its age, about its history, about the fact that it was not always as it is now. Tonight we are going to follow this question honestly. We will not stop at because the stars are far away, because that is an incomplete answer. We will arrive at what is called Olbers' paradox, one of the most beautiful paradoxes in the history of science, and at what its resolution told us about the very nature of the universe. If the night is long, stay. Let us begin with the question stated precisely. Not simply, why is it dark, but why is it dark if stars are everywhere? Imagine you are standing in a forest, a dense forest with trees in every direction. If the forest is large enough, in whatever direction you look, your line of sight will eventually hit a tree trunk. Not the space between trees, the tree itself. Because there are enough trees to cover every angle of view. Now replace trees with stars. If the universe is infinite and stars are uniformly distributed through it, then in whatever direction you look, your line of sight should eventually end on a star. Every line of sight should terminate at the surface of a star. If every line of sight ends at the surface of a star, then every point on the night sky should be as bright as the surface of a star. At least as bright as the surface of the sun, because most stars are similar to the sun. The night sky should be a uniform blaze of light, as bright as the surface of the sun at every point, which would make night as bright as a full sunny day, or brighter. But the sky is black. This is called Olbers' paradox, named for German astronomer Heinrich Wilhelm Olbers, who formulated it in 1823. Though the question was raised earlier by Kepler in the 17th century, by Edmund Halley in the early 18th century, and by others. But Olbers' name stuck to this paradox in the history of science. The paradox is simple. If the universe is infinite and stars are uniformly distributed through it and have existed forever, the night sky should be blindingly bright, but it is black. Something is wrong with the premises. Let us talk about the first intuitive objection that probably comes to mind, that stars are far away, so their light is weaker. This is true, but it is not a solution to the paradox. Here is why. The brightness of a star decreases as the square of the distance. This is the well-known inverse square law. A star twice as far away is 4 times dimmer. A star 10 times as far is 100 times dimmer. But, and this is the key point, the number of stars at a given distance increases as the square of the distance. Stars at a distance from r to r plus d r fill a spherical shell with surface area proportional to r squared. If stars are uniformly distributed, this shell contains a number of stars proportional to r squared. The total light from all stars in a given spherical shell equals number of stars times brightness of each star is proportional to r squared times 1 over r squared equals constant. This means that every spherical shell, regardless of distance, contributes an equal amount to the total light arriving at us. The near shell and the far shell contribute equally. If there are infinitely many shells, their contributions sum to infinity. Distance alone does not solve the paradox. The decrease in brightness of each individual star is exactly compensated by the increase in the number of stars in distant shells. The total brightness of all stars in the universe, assuming the universe is infinite, uniform, and eternal, should be infinite. Or more concretely, if every line of sight ends on a star, the sky should be as bright as the surface of an average star. And the average star has a surface brightness comparable to the sun's surface. But the sky is black. Something is wrong. Let us talk about the various proposed solutions to the paradox throughout history, because the path to the correct answer through incorrect attempts is part of the history of science. First proposed solution. Dust and gas between stars absorb the light from distant stars. This seems reasonable. Interstellar space is not a perfect vacuum. There is gas and dust. Dust absorbs light. If distant stars are hidden behind dust clouds, they do not contribute to the brightness of the sky. The problem with this solution: dust heats up from the light it absorbs. Eventually, dust also radiates light in the infrared range. At equilibrium, absorption and emission balance out, and the total energy flux does not decrease. Moreover, if the universe is infinite and eternal, dust would have been heated to the temperature of stellar surfaces. Then the dust itself would glow as brightly as stars. The paradox would simply have shifted from stars to dust. Absorption does not solve the paradox, it just moves the problem. Second proposed solution. Stars are not uniformly distributed, they cluster in galaxies with enormous voids between them. This also seems reasonable. We do see that stars gather in galaxies, galaxies in clusters, clusters in filaments. Between these structures, vast voids. But this also does not solve the paradox if the universe is infinite and galaxies occupy a finite fraction of the volume of space. The same square argument works at the level of galaxies just as at the level of individual stars. Distant galaxies are dimmer, but there are more of them. The contribution of each spherical shell of galaxies to the total light is still constant. With infinitely many shells, the total light is still infinite. The clustering of stars into galaxies does not solve the paradox. Third proposal: the universe is finite. If stars occupy a finite volume of space, a finite number of stellar shells exist, the total contribution is finite and the sky can be dark. This is the solution Olbers himself accepted as correct. He assumed the universe is finite, that stars fill a finite volume, and therefore the sky is dark. But this is also not the complete solution, or rather it is a solution for a slightly different reason than Olbers thought. Modern observational astronomy has shown that the universe is not finite in the sense that stars simply end at some distance. The universe is homogeneous on large scales, roughly the same number of galaxies and stars in every direction out to as far as we can observe. The true solution to the paradox is different, and it has to do not with space, but with time. Let us talk about the correct solution to Olbers' paradox, about what the dark night sky tells us about the age and history of the universe. The true solution was understood in the 20th century after the discovery of the expansion of the universe. The universe is not eternal, it has an age. The Big Bang occurred about 13.8 billion years ago. This means the oldest light we can in principle receive, light that has been travelling toward us since the Big Bang, has had 13.8 billion years to reach us. The speed of light is finite, about 300,000 kilometers per second. In 13.8 billion years, light can travel about 13.8 billion light years. Taking into account the expansion of the universe, the observable universe is somewhat larger, about 46 billion light years in radius, but this does not change the principle. This means we see only a finite part of the universe, the part within our light horizon. Stars and galaxies beyond this horizon we do not see, simply because their light has not yet reached us. Not because they are not there, but because the universe has existed for a finite time. The key point: if the universe has existed for a finite time, then the number of spherical shells from which we can receive light is finite. and the total contribution of all these shells to the brightness of the sky is finite. But even this explanation is not sufficient for a complete answer. Because 13.8 billion years is a very long time, it might seem enough for light to have accumulated to a brightness comparable to sunlight. The second important component of the solution, the expansion of the universe. The universe is expanding. This means that light from distant galaxies is redshifted, its wavelength stretched due to the expansion of space. Redshifted light carries less energy. Distant galaxies, however many there are, appear dimmer, not only because of distance, but because of redshift. Moreover, the expansion of the universe means that the most distant objects are moving away from us. Photons that they emitted and that are travelling toward us travel through expanding space. The distance they need to cover increases as they travel. Some objects are moving away so fast that their light will never reach us. This creates a real horizon. Not only the light horizon, determined by the age of the universe, but the Hubble horizon, determined by the rate of expansion. Objects beyond the Hubble horizon are moving away faster than light. Their radiation will never reach us. Let us talk about what is the most beautiful aspect of this solution, about how the dark night sky is direct evidence that the universe is young. This seems counterintuitive. We look at a dark sky and conclude about the age of the universe? Yes, exactly this. If the universe were eternal, if it had existed infinitely long and stars had burned in it forever, the sky would be blindingly bright. Light from countless stars would have accumulated over infinite time and filled all space to the brightness level of a stellar surface. That the sky is dark, this is proof that the universe has existed for a finite time, that light has had only finite time to travel, that the number of shells from which we can receive light is finite. The dark night sky is observational evidence that the universe has a beginning. Edgar Allan Poe, a poet, not a scientist, was one of the first to formulate this correctly. In 1848, in the essay Eureka, he wrote that the darkness of the night sky is explained by the universe being of finite age. Light from infinitely distant stars has simply not had time to reach us. Poe was a poet who anticipated a scientific conclusion that would be reached more than 100 years later. The correct answer was assembled in the 20th century, after Hubble's 1929 observation that galaxies are moving away from us, and after the development of Big Bang theory, which gave the universe a specific age. Let us now talk about the specific numbers, about how bright the night sky would be if the paradox were not resolved. The surface brightness of the Sun is about 2 × 10⁹ candelas per square metre. If the entire night sky were as bright as the Sun's surface, the total radiation intensity received by Earth would be roughly 400,000 times what we currently receive from the Sun. This is because the sky covers the entire sky, a solid angle of 4 pi steradians, while the Sun occupies only a tiny fraction of it. At this radiation intensity, the surface of Earth would heat to a temperature of several thousand degrees Celsius. Nothing would survive. No water, no life, no solid crust, just superheated plasma. That the sky is dark is literally a condition for our existence. Let us now talk about the cosmic microwave background, because it is directly connected to Olbers' paradox and is the most direct observation of the echo of the Big Bang. The universe began as an extremely hot and dense plasma. All matter was ionized. Atoms could not form because the temperature was too high. Light photons were constantly scattered by free electrons. The universe was opaque. Light could not propagate freely. About 380,000 years after the Big Bang, the universe had expanded and cooled enough for electrons to combine with protons and hydrogen atoms to form. This is called the epoch of recombination. At this moment, the universe became transparent. Photons stopped scattering and began to propagate freely through space. Those same photons that were freely emitted at the moment of recombination 13.8 billion years ago are still traveling through the universe. But after 13.8 billion years of universal expansion, their wavelength has been stretched enormously. They began as visible light. Now they are microwave radiation. Their temperature is about 2.725 Kelvin, just above absolute zero. This is the cosmic microwave background, CMB. It arrives at us with equal intensity from all directions. This is literally the light of the first 380,000 years of the universe, frozen in the microwave range by the expansion of space. The CMB is a direct consequence of the same fact that resolves Olbers' paradox. The universe has a finite age and is expanding. If the universe were eternal and static, there would be no CMB. There would simply be a bright, stellar sky. The fact that we observe the CMB and that the night sky is dark are two observations of two sides of the same coin. The universe arose at a specific moment in time and has been expanding ever since. Let us now talk about what the resolution of Olbers' paradox means conceptually, about why an answer to such a simple question contains such a profound revelation. The question was, why is the night sky dark? The answer, because the universe has a finite age and is expanding. This is not a trivial conclusion. For most of the history of human thought, the universe was considered eternal and static. The idea that the universe had a beginning, that there was a time when it did not exist, seemed more like a religious concept than a scientific one. Olbers' paradox and its resolution showed that an observation as simple as the darkness of the night sky carries information about the cosmological history of the universe. That the answer to a child's question requires knowledge of the Big Bang. This is one of the most beautiful things in physics, when a simple observation that seems self-evident turns out to be a window into deep physical reality. When a question that a child might ask an adult requires an understanding of the origin and structure of the universe for its answer. Let us now talk about the Hubble discovery that gave us the correct solution, about what happened in 1929 and why it changed everything. Edwin Hubble was working at the Mount Wilson Observatory in California. He used what was then the world's largest telescope, a 100-inch reflector. With it, he could resolve individual stars in the nearest galaxies. In 1923 to 1924, Hubble observed a Cepheid variable star in the Andromeda Nebula. Cepheids are stars that pulsate with a period proportional to their luminosity. Knowing the period, you can determine the luminosity. Knowing the luminosity and the apparent brightness, you can determine the distance. The distance to the Andromeda Nebula that Hubble determined was far beyond the Milky Way. Andromeda turned out to be a separate galaxy, an independent island universe, as Immanuel Kant had suggested as long ago as 1755. In 1929, Hubble published an even more revolutionary result. Comparing distances to galaxies with their recession velocities, he found a linear relationship. The farther the galaxy, the faster it is receding. V equals h0 times d. This is Hubble's law. h0, the Hubble constant, is the constant of proportionality. Its current value is estimated at about 67 to 73 kilometers per second per megaparsec. Hubble's law means the universe is expanding. Not just that galaxies are moving in different directions, but that space itself between them is expanding. This is a fundamental distinction. Galaxies are not moving through space. space between them is growing. If space is expanding, in the past it was compressed. Continuing backward far enough, all matter and all energy were concentrated in an infinitely small volume. This is the beginning of the universe, the Big Bang. And here the circle of Olbers' paradox closes. Hubble's discovery gave the solution to a paradox that had troubled astronomers for more than 100 years. The sky is dark because the universe has a finite age, because it began in the Big Bang, and light from infinitely distant stars has simply not had time to reach us. One observation, the spectra of galaxies in a telescope, gave us simultaneously both the structure of the universe, it is expanding, and the explanation for the simplest phenomenon, the darkness of the night sky. Let us now talk about what the universe looks like when you look at the dark parts of the sky with modern instruments, about what the James Webb Space Telescope revealed about the darkness between stars. One of the most iconic images in the history of astronomy is the Hubble Deep Field from 1995. The Hubble team pointed the telescope at a small, apparently empty patch of sky, about 2.6 arc-minutes across, and exposed for 10 days. The resulting image showed about 3,000 galaxies in what appeared to be an empty spot. This was a shock. The empty sky turned out to be filled with galaxies visible with long enough exposure. Every small blob and smear in the image was a separate galaxy, each containing billions of stars. The James Webb Space Telescope went even further. JWST works primarily in the near and mid-infrared, which better penetrates dust and can detect light from the earliest galaxies that has been redshifted from ultraviolet and visible into infrared. JWST images have revealed galaxies that existed less than 400 million years after the Big Bang. All the empty sky, every region that appears black between visible stars, when exposed long enough with a sufficiently sensitive infrared telescope, fills with galaxies. Thousands of galaxies in every square degree of sky. The darkness of the night sky does not mean emptiness. It means that the light from most of the universe's galaxies is too faint and too redshifted to be visible without a very sensitive instrument. The light is there, an enormous amount of light, just not in the visible range and too faint for our eyes. If you add up all the light from all galaxies in the observable universe, it is not zero. There is a measurable background level of optical and infrared radiation from all galaxies within our horizon. This is called the extragalactic background light, EBL. It has been measured, it is real, but it is so faint and spread across the sky that our eyes cannot see it. We see only discrete bright objects standing out against this background. Let us now talk about the layers of the night sky, about what you are actually looking through when you look up at night. The night sky has structure at many scales simultaneously. When you look in any direction, you are looking through all of these layers at once. The nearest layer, zodiacal light. Dust in the plane of the solar system, from asteroid collisions and comet tails, scatters sunlight and produces a faint cone of light visible along the ecliptic from very dark locations. This is our local neighborhood, within a few astronomical units. The next layer, individual stars. The nearest are a few light years away. The Milky Way's disk of stars extends tens of thousands of light years. When you see the Milky Way band in the sky, you are looking at the disk of our galaxy from inside it. Hundreds of millions of stars merged into a haze because they are too far to resolve individually. Beyond that, nearby galaxies. The Magellanic Clouds, satellite galaxies of the Milky Way, are about 160,000 to 200,000 light-years away. The Andromeda Galaxy is 2.537 million light-years away, visible as a faint smudge to the naked eye from dark locations. Beyond that, the larger universe of galaxies, billions of galaxies extending to 13.8 billion light-years in every direction. These are invisible to the naked eye, but fill the dark patches between stars when observed with a telescope. And beyond all of that, the cosmic microwave background. The light from the epoch of recombination, 380,000 years after the Big Bang, 13.8 billion light-years away, the most distant thing we can observe. Beyond this wall of light, the universe was opaque and nothing can be seen. When you look at the night sky, you are simultaneously looking at objects at all these different distances, from dust grains in our solar system to the very limit of our observable universe, all of it present at once in your field of view. The darkness is simply what is there between the visible things, the photons that have not yet arrived, the light from objects beyond our horizon, the faint background that is below the threshold of your vision. Let us now talk about one of the most significant recent measurements related to the darkness of the night sky, about the precise measurement of the extragalactic background light. The EBL, the total light from all galaxies in the observable universe, can be measured. This is not a simple task. The EBL is extremely faint and difficult to separate from other background light sources such as zodiacal light, atmospheric air glow, and diffuse galactic light. The most precise measurements of the EBL came from an unexpected source, gamma-ray astronomy. High-energy gamma-ray photons traveling from distant sources interact with EBL photons through a process called pair production. A high-energy gamma photon plus an EBL photon produces an electron and a positron. This process absorbs gamma photons, and from the pattern of absorption, the spectrum and intensity of the EBL can be reconstructed. The Fermi Gamma Ray Space Telescope, launched in 2008, provided data that enabled, in 2012, the first sufficiently precise direct measurement of the EBL. Result? The total brightness of all galaxies in the observable universe corresponds to about 4 × 10⁻⁹ watts per square meter in the visible and ultraviolet range at Earth. For comparison, the total brightness of the night sky visible to the naked eye is about 10⁻⁷ watts per square meter, roughly 25 times brighter than the extragalactic background. These measurements also allowed calculation of the total number of photons produced by all stars in the universe throughout its history. This number is about 4 × 10⁴ power photons. Enormous, but finite. Finite number of photons over a finite time of universal existence. Finite brightness. Dark sky. Let us now talk about what the darkness of the night sky means for our understanding of where we are in time, about the specific epoch of the universe we inhabit. Before the discovery of cosmic expansion, before Hubble, before Big Bang theory, the prevailing picture was an eternal static universe. It had always been roughly as it is. It would always be roughly as it is. No beginning and no end. Stars burned forever. Galaxies always existed. In such a universe, humanity occupied an arbitrary place in space, but an arbitrary moment in the sense that all moments are equivalent. The universe is always the same. The discovery of expansion and finite age changed this. Now we know that we occupy not only a specific place in space, but a specific moment in history. We live about 13.8 billion years after the Big Bang. This is not an arbitrary moment. This is an epoch when stars still burn, when galaxies are still visible, when planets exist with the heavy elements necessary for chemistry and life. Before us was a period without stars, the first few 100 million years after the Big Bang, the dark ages of the universe. No stars to illuminate space, no planets, no chemical complexity. Life was impossible. After us will come an era of fading, when stars begin to go out one by one on timescales of trillions of years. Gradually, the universe will become darker, not because of its age, but because the sources are exhausted. We live in what might be called the golden age of the universe, an epoch when star formation still occurs, when stars of all generations shine, when the chemical enrichment of galaxies has reached the level that allows the existence of rocky planets with complex chemistry. The dark night sky, despite all the stars, is a symbol of this specific epoch. It is dark because the universe is young. It is dark because it has not had time to accumulate enough light. But it is bright enough, with specific stars that can be seen, because stars have already ignited. We are in the right epoch, after the Dark Ages, before the fading, in the age of stars. Let us now talk about what Olbers' paradox reveals about the nature of the questions we ask, about the pattern where the simplest observations conceal the deepest truths. Why is it dark at night? This is a question any child asks. It seems almost too simple to ask seriously. But this question, in the hands of Kepler, Halley, Olbers, Kelvin, Poe, Hubble, successively led to one of the most fundamental discoveries in the history of cosmology. The universe has a finite age. It is expanding. It began in the Big Bang. This pattern repeats throughout the history of science. The simplest questions often have the deepest answers. Why does an apple fall downward? Newton, gravity, planetary motion. A theory of gravitation applicable to the entire universe. Why is the speed of light the same for all observers? Einstein. Special relativity, E equals mc squared. The nature of space and time. Why doesn't the electron fall into the atomic nucleus? Quantum mechanics, the uncertainty principle, quantum numbers, chemistry, life. Why is it dark at night? The finite age of the universe, the Big Bang, expansion, the CMB, all of modern cosmology. Children ask good questions. Scientists take these questions seriously. The question about the darkness of the night sky is something any person looking at the sky on any night throughout all of human history could have asked. But the correct answer required the invention of the telescope, the development of spectroscopy, the discovery of redshift, the introduction of the concept of galaxies, the measurement of distances through Cepheids, the discovery of the expansion of the universe, the development of the theory of relativity, the formulation of Big Bang theory, the discovery of the CMB, the measurement of the Hubble constant, the discovery of accelerated expansion and dark energy. The entire arsenal of modern astrophysics and cosmology to answer a question a child asks. This is science in its most beautiful form. You take what seems obvious, you ask it honestly, you follow where it leads, and you discover that in the simplest things, the deepest truths are hidden. The darkness of the night sky was not just darkness, it was a question waiting for the right moment and the right people to reveal its depth. And the correct answer turned out to be, all of this happened. The universe began. It is expanding. We live in its specific epoch, young and full of stars. And all of this is written in the darkness between stars for those who know how to read it. Let us talk about something that connects Olbers' paradox to one of the most active frontiers in modern physics, about dark energy and what the accelerating expansion of the universe means for the long-term future of the night sky. In 1998, two independent research teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, announced a discovery that earned their leaders the Nobel Prize in Physics in 2011. The expansion of the universe is accelerating, not just continuing, accelerating. Galaxies are moving away from each other faster and faster. This was completely unexpected. Before this discovery, it was assumed that the expansion was slowing down due to the gravitational attraction between galaxies. The discovery of accelerated expansion required the introduction of dark energy, an unknown form of energy permeating space and creating a repulsive effect. What does this mean for the darkness of the night sky? Accelerated expansion means that distant galaxies are moving away from us at a rate that is increasing with time. Eventually, in the sufficiently distant future, the distance to most galaxies we currently see will become so large that their light will not reach us. They will disappear from our observable universe. More specifically, the event horizon created by dark energy means that galaxies beyond a certain distance from us are already receding faster than the speed of light. They have already slipped beyond our horizon. We still see their light because it was emitted when they were closer and slower, but new photons they emit now will never reach us. This means that over time the observable universe for any observer becomes smaller. Gradually, galaxies will disappear beyond the horizon one by one. In a few 100 billion years, if current rates of acceleration continue, the Milky Way and its gravitationally bound neighbours, the Andromeda Galaxy and a few dwarf galaxies of the local group, will be the only visible objects. Everything else would have vanished beyond the horizon. The sky will become even darker, from the perspective of extragalactic sources. A civilization living in our galaxy 1 trillion years from now will not be able to see what we see now. They will not know that other galaxies exist because all traces of that knowledge will have disappeared. This is one of the most existentially striking consequences of dark energy. We live in an epoch when most of the universe is still visible. In the future, it will become invisible. Not because it will disappear, but because the expansion will carry it beyond our horizon. We live in a privileged time, when the universe is still young and compact enough that we can see most of it. Future observers, existing billions of years after us, will have a dramatically more limited view. Let us now talk about what happens if you think about the night sky not just as a visual phenomenon, but as a window across all of time simultaneously. When you look at the moon, you see it as it was 1.3 seconds ago. Light travelled 1.3 seconds. When you look at the sun, you see it as it was 8 minutes ago. When you look at Alpha Centauri, the nearest star, you see it as it was 4.37 years ago. When you look at the Andromeda Galaxy, the nearest large galaxy, you see it as it was 2.537 million years ago. At that time on Earth lived our ancestors Homo habilis. When astronomers with JWST look at the most distant galaxies, they see galaxies as they were about 13.4 billion years ago, when the universe was less than 400 million years old. To look far is to look into the past. This is a literal physical reality, not a metaphor. Light that reaches your eye from a distant object carries information about the state of that object in the past. The farther the object, the farther into the past you are looking. This means the night sky is simultaneously a spatial and temporal landscape. Different stars you see at the same moment existed in different epochs when their light was emitted. The nearest star you see shows you its past from a few years ago. A distant galaxy shows you billions of years ago. They all exist for you simultaneously, but in different time epochs. Precisely because the speed of light is finite, and precisely because the universe has a finite age, there is a horizon beyond which we can see nothing. Beyond 13.8 billion light years, the boundary of the observable universe. What lies beyond this boundary is invisible not because there is nothing there, but because their light has not had time to arrive. This is exactly what makes the sky dark. Let us now talk about a specific thought experiment that makes the resolution of Olbers' paradox concretely intuitive. Imagine you are standing in a very large forest at night. Every tree has a flashing lantern that turns on once per minute. Light from each lantern travels at, say, 100 meters per second. If the forest has existed for 1 minute, you see only the lanterns of trees within 100 meters of you. Trees farther away have not yet sent you their first pulse. The sky, imagining the trees illuminate in all directions, will be quite dark. Only the nearest trees within 100 meters. If the forest has existed for 10 minutes, you see lanterns within 1,000 meters. More trees, brighter. If the forest has existed for 1 million minutes, you see lanterns at 100 million meters. A vast number of trees, the sky significantly brighter. If the forest has existed forever, you see lanterns infinitely far away. Infinite number of trees, the sky infinitely bright. The universe works exactly this way. Except instead of 100 meters per second, the speed of light at 300,000 kilometers per second, and instead of 1 minute, 13.8 billion years. In 13.8 billion years, light has had time to reach us from about 13.8 billion light years away. All stars beyond this horizon, their light is still in transit. They have not contributed their share to the brightness of our sky, hence the darkness. This is not a metaphor, this is literally what is happening. Photons from stars beyond our horizon are now traveling toward us, but have not yet arrived. Through billions of years, the sky will become slightly brighter because more sources will have had time to send us their photons. The universe is dark because it is young, not because space is empty or because stars are faint, but because light has had only finite time to travel. Let us now talk about the specific connection between the darkness of the night sky and the second law of thermodynamics, because this is one of the deepest physical connections in this story. Entropy is a measure of disorder, or more precisely, a measure of the number of possible microstates of a system. The second law of thermodynamics states that the entropy of a closed system never decreases. It either stays constant or increases. In physical terms, this means that over time, everything tends toward equilibrium. A hot object in contact with a cold one cools down. Concentrated energy disperses. Ordered structures degrade into disorder. If the universe were eternal and static, it should long ago have reached thermodynamic equilibrium. All energy sources would be exhausted. Temperature everywhere would be uniform. No stars, no planets, no life. Just uniformly distributed heat. This is called the heat death of the universe. The fact that we see stars, that there are sources of light and heat, that temperature gradients exist between hot stars and cold space, is evidence that the universe has not reached equilibrium, that it has not had infinite time for this. The connection to Olbers' paradox: if the sky were as bright as the surface of a star, this would mean the universe had reached thermodynamic equilibrium, where all energy is uniformly distributed at stellar surface temperature. In such a universe, there could be no life, because life exists through temperature differentials, through flows of energy from hot sources to cold sinks. The darkness of the night sky is simultaneously a consequence and a condition of the existence of life. A consequence, because dark sky means the universe is young and has not reached equilibrium. A condition, because only in a universe with a dark sky, with a cold radiation background and hot point stars, is the energy flow possible that drives biological processes. We exist not despite the sky being dark, but partly because it is dark. Let us now talk about one more layer of this story, about what it means that the specific value of the CMB temperature, 2.725 Kelvin, is itself a consequence of the history of expansion. At the moment of recombination, 380,000 years after the Big Bang, the temperature of the universe was about 3,000 Kelvin. This is hot enough to emit visible light, orange-red like a dim light bulb. In the 13.8 billion years since recombination, the universe has expanded by a factor of about 1,100. This expansion stretched all wavelengths of light by the same factor. Visible light with a wavelength of about 1 micrometer has been stretched to about 1.1 millimeters, the microwave range. The temperature of blackbody radiation is inversely proportional to wavelength. A temperature of 3,000 Kelvin divided by 1,100 gives approximately 2.73 Kelvin, matching the observed CMB temperature with precision. This calculation, taking the temperature at recombination, dividing by the expansion factor, arriving at the current CMB temperature, is a specific quantitative prediction of Big Bang cosmology. It was confirmed with extraordinary precision by the COBE, WMAP and Planck satellites. The fact that the prediction works, that the CMB temperature we measure today matches the prediction from the expansion factor and the temperature at recombination, is one of the strongest confirmations of our understanding of the universe's history. The darkness of the night sky is connected to this CMB temperature in a specific way. Both reflect the same underlying fact. The universe began in a hot, dense state and has been expanding and cooling ever since. The sky is dark because the expansion has been going on long enough to dilute and redshift the primordial light to invisibility. The CMB is what remains of that primordial light, stretched by the same expansion into microwave photons at 2.725 Kelvin. One expansion, two observational consequences: dark sky, faint microwave background. Let us now talk about what the totality of this story reveals when you look at it from the widest possible perspective, about what the darkness of the night sky says about the universe as a knowable place. The universe could have been arranged so that its fundamental properties were unknowable from inside it. It could have been arranged so that every observation was ambiguous, every signal swamped by noise, every pattern masked by randomness. There is no logical necessity that the universe be comprehensible to beings who evolved within it for entirely different reasons. And yet, the night sky is dark. This is a fact about the universe that is simple to observe. Any human who has ever looked up has seen it. And this simple, observable fact encodes within it the deepest truth about the universe's history: that it began, that it has been expanding, that it has a finite age. The universe is legible. The cosmos contains within its most immediate appearances the information needed to understand its origin. The darkness between the stars is not just decoration, it is a clue visible to any careful observer pointing toward the Big Bang. Kepler saw this clue and noted it in 1610. Olbers framed it as a paradox in 1823. Poe sensed the answer in 1848. Hubble gave the observational key in 1929. Penzias and Wilson found the acoustic echo in 1964. Generations of human beings, looking at the same dark sky you are looking at now, building understanding brick by brick across centuries, until the darkness itself yielded its meaning. The universe began. It has been expanding ever since. And the darkness of the night sky, that simple fact that every child notices, is written evidence of this, legible to anyone who asks the question seriously enough. Let us now talk about what this means for the sky you can observe tonight, about how knowing all of this transforms the experience of looking up. Find the darkest patch you can see between stars. not a star, the darkness between stars. In that direction, space extends 13.8 billion light-years to our observational horizon. Beyond that horizon, more space, possibly infinitely more. But that light is still in transit. You are looking at the edge of your accessible universe. This is not an abstraction. It is the literal physical reality of this specific point in space-time where you are standing right now. And what you see, darkness, is proof that the universe had a beginning. The simplest observation, the deepest answer. Every person who has ever lived has looked up at this same darkness. Egyptian astronomers building the pyramids, Greek philosophers mapping the constellations, Polynesian navigators crossing the Pacific, Copernicus, Galileo, Newton, all of them saw the same dark sky between the same stars. None of them had the full answer. The full answer required the technology to measure the redshifts of galaxies, the sensitivity to detect the CMB, the mathematics to work backward from an expanding universe to its origin. But the clue was always there, in plain sight, in the darkness itself, available to anyone who looked carefully and asked honestly. Why is it dark? The universe is dark at night because it had a beginning. Because 13.8 billion years ago, something happened. Something we call the Big Bang, though the words do not quite capture it. And since then, space has been expanding, and matter has been forming structures, and stars have been burning. And on at least one planet, around at least one star, beings have evolved who look up at the darkness and ask why. That question, why is it dark, and its answer, because the universe is young, form a loop. We exist to ask the question because the universe is young enough for stars to still burn. The universe is young enough for stars to still burn, and that is why the sky is dark. And the darkness of the sky is how we know the universe is young. The question contains its answer. The observation encodes the history. The darkness speaks. Let us talk about something specific that deepens the picture, about what the cosmic microwave background actually looks like in detail, and what the tiny variations in its temperature reveal about the structure of the universe. The CMB is not perfectly uniform. It is uniform to about 1 part in 100,000, but that tiny departure from perfect uniformity is one of the most scientifically rich datasets in all of cosmology. The temperature variations, hot spots and cold spots differing by about 0.00003 degrees Kelvin from the average, are the imprint of density fluctuations in the early universe at the moment of recombination. Slightly denser regions at the time of recombination corresponded to slightly hotter CMB, because the photons in those regions had to climb out of a slightly deeper gravitational well, losing a tiny bit of energy in the process. Slightly less dense regions corresponded to slightly cooler CMB. These density fluctuations at the time of recombination are the seeds of all the structures we see today. The slightly denser regions attracted more matter through gravity over billions of years, gradually forming proto-galaxies, then clusters of galaxies, then the vast cosmic web of filaments and voids that constitutes the large-scale structure of the universe. The slightly less dense regions evolved into voids, the enormous near-empty bubbles of space between the galactic filaments. Everything we see in the night sky, every galaxy, every cluster, every filament, was already sketched in outline in the tiny temperature variations of the CMB 13.8 billion years ago. The CMB is a baby picture of the universe, showing the seeds of all future structure. Measuring these fluctuations with precision tells us enormous amounts about the physics of the early universe. The specific pattern of hot and cold spots, their sizes, their amplitudes, their correlations, depends on the specific physical parameters of the universe. The total density, the fraction that is ordinary matter, the fraction that is dark matter, the fraction that is dark energy, the expansion rate, the geometry of space. By measuring the CMB pattern and comparing it to theoretical predictions, cosmologists have determined these parameters with remarkable precision. The universe is 13.8 billion years old. Ordinary matter comprises 5% of the total, dark matter about 27%, dark energy about 68%. Space is geometrically flat to within a fraction of a percent. All of this from measuring tiny variations in the temperature of a microwave background, the stretched and cooled echo of the light from the recombination epoch. And this light, the CMB, is what the darkness of the night sky would be filled with if our eyes could see microwaves. The darkness is not empty. It is filled with this faint, structured glow at 2.725 Kelvin, the most detailed portrait of the early universe we possess. Let us now talk about one of the most technically impressive demonstrations of what lies behind the dark night sky, about the Hubble Ultra-Deep Field and its successors. In 2003 to 2004, the Hubble Space Telescope team pointed the telescope at a tiny patch of apparently empty sky in the constellation Fornax. The patch was about 1/10 the diameter of the full moon. They exposed for approximately 11.3 days, about 1,000,000 seconds of total exposure time. The resulting image, the Hubble Ultra-Deep Field, is one of the most astonishing photographs ever taken. In a patch of sky smaller than a grain of sand held at arm's length, there are approximately 10,000 galaxies. Some are spirals like the Milky Way, some are ellipticals, some are irregular, distorted shapes from ancient collisions. The most distant ones are visible as tiny red smudges. The redshift has shifted their light so far toward the red that they barely appear in the visible range. Every single object in that image, with very few exceptions, is a galaxy, not a star. A galaxy containing anywhere from a few million to hundreds of billions of stars. A grain of sand held at arm's length. 10,000 galaxies. There are approximately 17,000 square degrees in the full sky. The Hubble Ultra-Deep Field covers about 11 square arc minutes, roughly 1/13 millionth of the full sky. If the universe were uniform, which it approximately is on large scales, there would be roughly 10,000 times 13 million equals 130 billion galaxies visible to Hubble. More recent estimates, accounting for galaxies too faint for Hubble to detect, push the total number in the observable universe to around 2 trillion. The darkness between the stars is not just a few bright objects with space between them. It is a fabric of galaxies, so numerous, so distant, so faint that they blend together into an invisible background through which only the nearest and brightest are visible without optical aid. And behind the galaxies, the CMB. And behind the CMB, the opaque wall of the recombination epoch. And beyond that, the universe as it was in its first 380,000 years, before light could travel freely. And beyond that, the Big Bang itself, the moment of beginning. The darkness of the night sky is a window cut through all of this, or rather, the limit of what we can see through this window. The window extends 13.8 billion light-years in every direction. Beyond the window, more universe, beyond reach. Let us now talk about the specific role that light pollution plays in our relationship with this window, and what we lose when we lose access to the dark sky. About 80% of the world's population now lives under skies bright enough to obscure the Milky Way. In North America and Europe, the fraction is higher still. More than 99% of people in these regions live under light-polluted skies. In many cities, a typical person can see perhaps a few dozen stars on a clear night. This is historically extraordinary. For the entirety of human history before the 20th century, every person who ever lived had access to the full night sky. The Milky Way was not something you had to travel to see, it was simply what the sky looked like at night. Tens of millions of stars, the zodiacal light, the occasional meteor, the motion of planets against the stars, the seasonal rising and setting of constellations. This sky shaped human culture in ways we can barely reconstruct now. Navigation, calendar, mythology, the earliest astronomy, the earliest understanding that we are not at the center of the universe, that the moon orbits Earth, that Earth orbits the sun, that the stars are distant suns. All of this came from looking at a sky that most people living today have never seen in its full form. The loss is not only cultural and aesthetic, it is scientific. Many amateur astronomers have contributed genuine discoveries by monitoring variable stars, detecting novae, tracking asteroid positions. The distributed observing network of amateur astronomers around the world is a real scientific resource that depends on accessible dark skies. And it is psychological. The research we discussed earlier on awe as a psychological state, the broadening of perspective, the reduction of ego-centered thinking, the sense of connection to something larger than oneself, depends on actually having access to the experience that produces it. You cannot have the awe of the night sky from a sky with 40 visible stars. Olber's paradox, the question about why the sky is dark, becomes poignant in this context. The answer we now know is one of the deepest in science. But to even notice the question, to even think about it, to even have the experience of a genuinely dark sky worth asking about, requires access to a sky that most people no longer have. The darkness itself is being lost, and with it, the question, and with the question, the path toward the answer. Let us now talk about specific things you can see with your own eyes on a dark, clear night that illustrate different aspects of what we have been discussing. A kind of sky tour through the themes of tonight. The zodiacal light, visible from dark sites as a faint cone extending from the western horizon upward along the ecliptic after evening twilight. This is sunlight scattered by interplanetary dust, the most local phenomenon in the night sky. It represents the innermost layer of the universe you are looking through. The Milky Way. If visible, the diffuse band stretching from horizon to horizon is the disk of our galaxy, seen edge-on from inside. You are looking at a structure roughly 100,000 light-years across. The center of the galaxy, in the direction of Sagittarius, is about 26,000 light-years away. The dust clouds that make the inner galaxy appear patchy are themselves thousands of light-years away. You are already looking at distances that took light tens of thousands of years to cover. Individual bright stars, most of what you see individually, are within a few hundred light-years. Sirius, the brightest star in the night sky, is 8.6 light-years away. The light reaching your eyes from Sirius tonight left it about 8 years ago. Rigel in Orion, one of the most luminous stars visible, is about 860 light-years away. The light reaching you from Rigel left during the Middle Ages. The Andromeda Galaxy, the farthest object visible to the naked eye, a faint, elongated smudge in the constellation Andromeda, 2.537 million light-years away. The light reaching you from Andromeda left when our ancestors, Homo habilis, were making their first stone tools. When you look at Andromeda, you are seeing the universe as it was 2.5 million years ago with your naked eye. The darkness between all of these, behind every dark patch, lie thousands of galaxies invisible to your eye. The nearest of these unresolved galaxies are tens of millions of light years away. The most distant, in the deep fields accessed by Hubble and JWST, are more than 13 billion light years. All of this is present in the darkness you see between the stars. And pervading everything, the CMB at 2.725 Kelvin, arriving uniformly from all directions, invisible to your eyes but measurable by the right instruments, carrying information from 13.8 billion years ago. All of this simultaneously present in the sky above you right now. You are looking through 13.8 billion years of cosmic history, from the zodiacal dust in our solar neighborhood to the wall of the last scattering surface, every time you look at the night sky. Let us now talk about the remarkable fact that the darkness of the night sky, this seemingly passive, featureless backdrop, has been one of the primary drivers of cosmological discovery. The darkness prompted Kepler and later Olbers to notice the paradox. The paradox prompted the search for a resolution. The resolution pointed to a finite age and expanding universe. The expanding universe implied a beginning. The beginning implied residual radiation. The residual radiation, the CMB, was found by Penzias and Wilson in 1964. The CMB fluctuations revealed by COBE in 1992 pointed to the seeds of structure. The structure of those seeds, measured by WMAP and Planck, determined the precise parameters of cosmology. This chain of discovery, from the observation of darkness to the precision cosmology of the 21st century, spans 4 centuries. Each step followed inevitably from the previous. The darkness asked the question. The question demanded an answer. The answer required observations. The observations revealed structure. The structure demanded explanation. The explanation became precision cosmology. This is science working as it should, from observation to question to hypothesis to test to refined understanding. And the original observation was simply, why is it dark? The universe answered, because I am young, because I began, because I am expanding, because there is more of me beyond what you can see. All of this encoded in the darkness between the stars. Let us now talk about one final specific thing, about what looking at the night sky honestly and carefully actually tells you about your place in this universe. You are on a rocky planet, orbiting a star 4.6 billion years old, in a galaxy 100,000 light years across, in a local group of galaxies gravitationally bound together, in a supercluster, in an observable universe 46 billion light years in radius, that began 13.8 billion years ago in what we call the Big Bang. You are made of atoms forged in earlier generations of stars. The carbon in your cells, the oxygen in your blood, the calcium in your bones. These elements were synthesized in stellar cores through nuclear fusion, then distributed across space when those stars died in supernovae. You are literally made of stardust. Not metaphorically, but chemically, physically, precisely. You exist in a specific moment in the history of the universe, not arbitrary, but constrained. You exist after the epoch of first star formation, which produced the heavy elements needed for your chemistry. You exist before the far future epoch when all stars will have gone dark. You exist in the window of stellar life, the window of chemistry, the window of biology. You are here because you can be here. Because the universe is old enough to have made you, young enough to still be running, and arranged precisely enough, with the right constants, the right expansion rate, the right dark energy value, that complex structures can form and persist long enough to ask questions. And among the questions you can ask, looking up at the night sky, is one of the oldest and simplest. Why is it dark? And the answer reaches back to the beginning of time. The sky is dark because the universe had a beginning. Because light travels at a finite speed, because the universe is expanding, because the echo of the beginning fills space at 2.725 Kelvin in every direction. Because you live in the age of stars, after the dark ages, before the long darkness. The darkness between the stars is not absence, it is presence. The presence of a finite history, a young universe, a cosmos that has not yet had time to fill every direction of your sight with light. It is evidence available to every naked eye that has ever looked at the night sky that the universe began. Step outside tonight. Let your eyes adapt. Find the darkness between the stars. That darkness is the most ancient thing you will ever see. The shadow of the Big Bang itself. The absence of light from a universe too young to have sent it all to you yet. And it is available to you any clear night. No telescope required, just patience. And a willingness to ask, why is it dark? Let us talk about something that connects the darkness of the night sky to the most fundamental question in physics, about why there is something rather than nothing, and about what the Big Bang actually was. We have been talking about the Big Bang as the beginning of the universe, but what does this mean precisely? What was there before the Big Bang? What caused it? These are questions that physics can approach, but not yet fully answer. They sit at the boundary between what we know and what we do not know. But the darkness of the night sky, and its implication that the universe has a finite age, is what forces us to confront them. The standard Big Bang model describes the earliest state of the universe we can meaningfully discuss as a hot, dense plasma. The conditions that existed when the universe was about 1 second old or younger. The equations of general relativity, extended backward toward the moment of the Big Bang, encounter a singularity, a point where the density and temperature become mathematically infinite and the equations break down. A singularity is not a physical thing. It is a signal that the theory is being pushed beyond its domain of validity. General relativity does not account for quantum effects, which become important at the extreme densities and temperatures of the very early universe. A complete theory of quantum gravity, which we do not yet have, would presumably replace the singularity with something physically meaningful and mathematically well-defined. What this means practically: we do not know what happened at or before the Big Bang in any precise scientific sense. The question, why did the Big Bang happen, or what was there before, is currently unanswerable by physics. Not permanently unanswerable, but unanswerable with current theories. Several speculative frameworks exist. In quantum cosmology, pioneered by Stephen Hawking and James Hartle in the 1980s, the universe has no boundary in time. The beginning of time is smooth and rounded like the surface of a sphere, not a sharp edge. In this picture, asking what came before the Big Bang is like asking what is south of the South Pole. The question has no answer because there is no before. In eternal inflation, an extension of inflationary cosmology in which inflation is a generic and ongoing process, our Big Bang was one bubble nucleation in an eternally inflating space-time. Other bubble universes exist, each potentially with different physical constants. Our observable universe is one among infinitely many. In loop quantum cosmology, an application of loop quantum gravity to cosmology, the singularity of the Big Bang is replaced by a quantum bounce. Before the bounce was a contracting universe that reached a minimum volume and then began expanding. Our universe is one phase in an eternal alternation of contraction and expansion. None of these frameworks is observationally confirmed. None has the status of established science. They are theoretical explorations of what might lie at and beyond the limit of our current knowledge. But they all share one feature. They all start from the recognition forced on us by the darkness of the night sky. The universe had a beginning, or at least a phase transition that distinguishes before from after in a way that matters for everything we observe. And that beginning is something that demands understanding. The darkness of the night sky does not answer these questions, but it is what makes them unavoidable. If the sky were eternal and bright, there would be no question. The universe would be eternal and static, and there would be no beginning to ask about. The darkness forces the beginning, and the beginning forces the hardest question in cosmology. Why is there something rather than nothing? We do not know. But the darkness of the night sky is the observation that made us ask. Let us now talk about the specific physical process that connects the darkness of the night sky to the formation of the first stars, about the cosmic dark ages and how they ended. After recombination, after the universe became transparent and the CMB was released, there were no stars. The universe was filled with neutral hydrogen and helium gas, gradually cooling and expanding. There was no light source of any kind other than the fading CMB. The universe was truly dark. This epoch is called the Cosmic Dark Ages. It lasted from recombination at about 380,000 years after the Big Bang until the formation of the first stars at about 100 to 200 million years after the Big Bang. For approximately 100 to 200 million years, the universe had no luminous objects, no stars, no galaxies, no quasars, just expanding darkness filled with gas. The CMB was the only radiation. As the universe expanded, this background cooled further. The universe entered a phase darker than any darkness accessible in our current universe. There were no stars to look at, no galaxies to observe, just gas, dark matter, and the fading microwave background. This period is sometimes called the Dark Ages because no light was being emitted by stars or other stellar objects. It is also sometimes called the pre-stellar era. Then, very gradually at first, gravity began to amplify the tiny density fluctuations that were already present at recombination. Regions slightly denser than average began to contract. Dark matter halos formed first, providing gravitational wells for ordinary matter to fall into. Gas accumulated, cooled through radiation, and eventually reached the conditions needed for nuclear fusion to ignite. The first stars were probably very different from stars today. They formed in an environment with essentially no elements heavier than hydrogen and helium, the only elements produced in the Big Bang itself. Without heavy elements to facilitate cooling, the gas collapsed into very massive objects, probably hundreds to thousands of times the mass of the Sun. These massive stars burned very hot and very briefly, perhaps only a few million years, before exploding as supernovae and seeding the universe with the first heavy elements. The ionizing radiation from these first massive stars began to reionize the surrounding hydrogen gas, creating bubbles of ionized gas that gradually expanded and merged until the entire universe was reionized. This epoch of reionization lasted from about 200 million to about 1 billion years after the Big Bang. The James Webb Space Telescope is specifically designed to observe this epoch. Its infrared sensitivity allows it to detect the light from the earliest galaxies that formed near the end of the Dark Ages. The most distant galaxies JWST has observed existed when the universe was only about 300 to 400 million years old, right at the transition from the Dark Ages to the era of first stars. The darkness of the night sky today is intimately connected to the Dark Ages. During the Dark Ages, there were literally no stars to light the universe. Today, there are trillions. The transition from one state to the other, from cosmic darkness to cosmic illumination, is one of the most dramatic transitions in the history of the universe, and it is one that we are now beginning to observe directly with JWST. Let us now talk about the specific way that the darkness of the night sky is connected to biology, about why life requires a dark sky, and how the physics of the CMB underlies the thermodynamics of living organisms. Life on Earth, and presumably any life that operates on similar thermodynamic principles, is fundamentally a machine for extracting useful work from energy flows. Specifically, life captures high-quality energy from a hot source and releases low-quality energy to a cold sink. The difference between the quality of the incoming and outgoing energy, the entropy increase, is what drives all biological processes. For life on Earth, the hot source is the Sun, a black body at about 5,778 Kelvin. The cold sink is the night sky, radiating heat to the CMB at 2.725 Kelvin. The enormous temperature difference between these two, about 5,775 Kelvin, is what makes life thermodynamically possible. Photosynthesis captures photons from the sun and uses their energy to build complex molecules. Animals eat plants and extract the stored chemical energy. At every step, energy is being degraded from high-quality, visible photons from a 5,778 Kelvin source to low-quality, infrared photons radiated into a 2.725 Kelvin background. The darkness of the night sky, the cold 2.725 Kelvin background, is the cold sink that makes this thermodynamic machine work. If the night sky were as bright as the surface of the sun at 5,778 Kelvin, there would be no temperature differential. Energy flowing from the sun to Earth would be immediately offset by equal energy arriving from all other directions. No gradient, no useful work, no life. If the night sky were at, say, 100 Kelvin instead of 2.725 Kelvin, it would be colder than 2.725 Kelvin from the CMB, only if we were inside some very cold enclosed structure. The point is that the colder the background, the larger the temperature differential with the sun, and the more efficient life's thermodynamic engine can be. The CMB at 2.725 Kelvin is almost as cold as anything can be, within a few degrees of absolute zero. This makes it the most effective possible cold sink for thermodynamic processes, and thus the most favourable possible background for life. The darkness of the night sky, and specifically its temperature of 2.725 Kelvin, is therefore not just a cosmological curiosity. It is a prerequisite for the thermodynamic processes that underlie all life as we know it. Life exists because the sky is dark, because the sky is cold, because the universe is young enough that the CMB has cooled to near absolute zero while the sun still burns at nearly 6,000 Kelvin. We are thermodynamic beings living in a thermodynamically favourable universe, and the night sky's darkness is the most direct observable evidence of this favourability. Let us now talk about something that is both technically specific and philosophically profound, about the Boltzmann brain problem and what it tells us about the darkness of the night sky as a sign that we live in a special moment. Ludwig Boltzmann, the great 19th century Austrian physicist who developed statistical mechanics, wrestled with a deep problem. His statistical mechanics described the evolution of systems from ordered low-entropy states to disordered high-entropy states. But if the universe had existed for infinite time in statistical equilibrium, how did it come to be in the extraordinarily low-entropy state we observe today? Boltzmann's tentative answer: in an eternally existing universe at thermodynamic equilibrium, random fluctuations could occasionally produce temporary order. Our entire observable universe, including all its stars and galaxies and planets and life, might be an extraordinarily improbable fluctuation from a background state of maximum entropy. This creates the Boltzmann brain problem. If order arises from random fluctuations in an eternal equilibrium universe, then small fluctuations are far more probable than large ones. A random fluctuation that produces a single, isolated brain with false memories of a coherent universe is vastly more probable than a fluctuation that produces an entire, coherent universe with the history we seem to remember. If we are Boltzmann's fluctuations, random statistical accidents, we are far more likely to be a single Boltzmann brain than to be observers in a real cosmic history. But we observe a universe that is not a minimum fluctuation. We observe a universe with consistent physical laws, a consistent history, a coherent CMB, a consistent expansion rate, consistent isotopic abundances. This is far more than a minimum fluctuation would produce. The resolution. We are not Boltzmann brains. We are real observers in a real universe that began in a genuinely low entropy state 13.8 billion years ago. The darkness of the night sky, and specifically the structure of the CMB, confirms this. The pattern of CMB fluctuations is exactly what is predicted by inflation, followed by hot Big Bang cosmology. It is not the pattern of a random fluctuation. It is the pattern of a specific physical process with a specific history. The darkness of the night sky is therefore also evidence against the Boltzmann brain scenario. It tells us the universe is not a random fluctuation from eternal equilibrium. It is the product of a specific history beginning from a specific low-entropy initial state. We are real. The history is real. The beginning happened. And the darkness between the stars and the faint structured glow of the CMB pervading that darkness is the most direct evidence of all of this. Let us now talk about what the specific structure of the dark sky reveals when viewed through the lens of information theory, about the information content of the night sky, and what it means that the darkness encodes a message. Information theory, developed by Claude Shannon in the 1940s, provides a mathematical framework for quantifying information. The information content of a message is related to how surprising it is, how much it reduces uncertainty. A message that tells you something you already knew with certainty contains zero information. A message that tells you something completely unexpected contains maximal information. The night sky, viewed as an information source, carries information about the universe at every scale. The positions and brightnesses of individual stars carry information about stellar populations, distances, and the structure of the Milky Way. The distribution of galaxies carries information about the large-scale structure of the universe and the history of structure formation. The spectrum of individual objects, their redshifts, carries information about distances and the expansion history. The CMB temperature fluctuations carry information about the conditions at recombination and the parameters of cosmological models. But the overall darkness of the sky, the fact that the background level of light is low rather than high, also carries information. Specifically, it carries the information that the universe has a finite age. In the language of information theory, the darkness is a signal that reduces uncertainty about the age and history of the universe. Before Olbers, the finite age was not known. The darkness of the sky, interpreted correctly, reduces uncertainty about this enormously. The night sky is not just a collection of bright objects against a dark background. It is a message. The universe communicating its history to any observer patient enough to read it. The darkness itself is part of the message. The positions and brightnesses of galaxies are part of the message. The CMB structure is part of the message. We have spent the last century learning to read this message. We now know the universe's age, composition, geometry, and expansion history to remarkable precision, all from information encoded in the night sky and its darkness. The universe is not silent. It is continuously broadcasting its history to any observer with the right instruments and the right questions. The darkness is not the absence of signal. It is the signal. Let us now talk about something that reveals how far we have come and how far we still have to go, about the open questions that remain even after resolving Olbers' paradox and establishing the standard cosmological model. The standard model of cosmology, lambda CDM, where lambda represents dark energy and CDM represents cold dark matter, is extraordinarily successful. It predicts the CMB spectrum and fluctuations to precision better than 1%. It predicts the large-scale structure of the universe, the distribution of galaxies and voids, in impressive quantitative detail. It predicts the abundances of light elements produced in Big Bang nucleosynthesis, hydrogen, helium, lithium, with good accuracy. But it contains components we do not understand at a fundamental level. Dark matter. We know it exists, from galaxy rotation curves, gravitational lensing, CMB fluctuations, and many other observations. We know its abundance, about 27% of the total energy content of the universe. We know it clusters gravitationally, but we do not know what it is. The most popular candidates, WIMPs, weakly interacting massive particles, have been searched for in underground detectors for decades without detection. Axions, another candidate, are being searched for with increasing sensitivity. Primordial black holes have been proposed. None is confirmed. Dark energy, even more mysterious than dark matter. It comprises about 68% of the total energy content. It is causing the expansion of the universe to accelerate. Its density appears constant, or nearly so, as the universe expands, which is a very unusual property for any physical substance. It has no known particle physics explanation. The theoretical prediction of the vacuum energy from quantum field theory, which should act like dark energy, is off from the observed value by a factor of 10 to the power of 120. This is often described as the worst prediction in the history of physics. The Hubble tension. Different methods of measuring the current expansion rate of the universe give different results. Measurements based on the CMB, early universe, and measurements based on Cepheid variables and Type 1a supernovae, late universe, disagree by about 5 to 10%. This discrepancy is now at about 5 standard deviations, enough to suggest it is not statistical noise, but might indicate new physics that our current model does not include. The nature of the Big Bang singularity. We do not have a theory of quantum gravity that resolves the singularity at the Big Bang. We do not know what actually happened at or before the Big Bang. Inflation, the rapid exponential expansion believed to have occurred in the first tiny fraction of a second, explains many features of the universe, but is not derived from a fundamental theory. It is a parametric description of what happened rather than an explanation of why it happened. These are not minor loose ends. They are fundamental unknowns at the heart of our understanding of the universe. The standard cosmological model, as successful as it is known to be incomplete. The darkness of the night sky led us to the Big Bang. The Big Bang led us to the CMB. The CMB led us to precision cosmology. Precision cosmology revealed dark matter and dark energy. And dark matter and dark energy remain mysterious. The darkness between the stars is still asking questions, still pointing toward unknown physics, still inviting deeper investigation. Let us now talk about a specific and beautiful consequence of the finite age of the universe that is rarely discussed, about the fact that our observable universe is unique to our location in space and time. Every observer in the universe has their own observable universe, the sphere of space from which light has had time to reach them since the Big Bang. An observer in the Andromeda galaxy has a slightly different observable universe from ours, overlapping almost completely but shifted by 2.537 million light-years. An observer near the edge of our observable universe, in one of the most distant galaxies JWST can see, has an observable universe that is mostly different from ours. They can see regions of space that are beyond our horizon. We can see regions of space that are beyond their horizon. We are in each other's observable universes only barely. They are near the edge of what we can see. We are near the edge of what they can see. This means the observable universe is not a feature of the universe itself. It is a feature of where and when you are located within it. The same universe looks different, includes different galaxies, different cosmic structure, to observers at different positions and different times. The universe as we see it, with the CMB in the far background, with specific galaxies at specific distances, with specific voids in specific directions, is a view unique to our location in space and time. An astronomer in a galaxy 1 billion light years away sees a different observable universe. An astronomer 1 trillion years from now will see a smaller observable universe. Many galaxies we see will have receded beyond their horizon. Our view of the universe, including the specific darkness of our night sky and the specific pattern of our CMB, is ours alone. It is as particular to our location as a fingerprint. This does not mean it is arbitrary or subjective. The physical laws are the same everywhere, and the universe is homogeneous on large scales. But the specific slice of the universe accessible to any particular observer is unique. We see what we see because we are where we are, when we are. The darkness of our night sky is our sky's darkness. The darkness appropriate to an observer in the Milky Way, 13.8 billion years after the Big Bang, at this specific moment in cosmic history. In the far future, this sky will look different. In the far past, when the universe was young and dense and the CMB was bright, it looked very different. In a different galaxy, in a different location, it looks different now. What we see tonight, what you see when you look at the dark sky, is a specific view available to a specific set of observers at a specific moment. That specificity, that particularity, is not a limitation. It is what makes the night sky yours, what makes the darkness yours to see and to wonder about. Let us talk about something that is both technically specific and immediately observable, about what the darkness of the night sky looks like when you examine it with different instruments, and what each reveals about a different layer of the universe. A human eye adapted to darkness in a truly dark location can see stars down to about magnitude 6.5. This includes roughly 9,000 to 10,000 stars visible across the full sky. It includes the Milky Way as a diffuse band. It includes the Andromeda Galaxy as a faint smudge. It includes the Magellanic Clouds from the southern hemisphere. Everything else is darkness. Binoculars at 10 times magnification reveal stars down to about magnitude 9 to 10, roughly 10 to 20 times more stars than the naked eye. More details of the Milky Way. Hints of structure in some nebulae. A few galaxies resolvable as clearly non-stellar objects. Still mostly darkness between objects. A small telescope, 80 to 100 mm aperture, reveals stars to about magnitude 12. Thousands more stars. Galaxies visible as distinct smudges in dozens of directions. Globular clusters, dense spherical gatherings of hundreds of thousands of stars, resolved from fuzzy balls into something approaching individual stars at the edges. Nebulae showing their structure. The darkness begins to look less like emptiness and more like a texture with faint things in every direction. A 200 to 250 mm amateur telescope reaches magnitude 13 to 14. Hundreds of galaxies visible. The Virgo cluster, a dense congregation of galaxies about 65 million light-years away, becomes an astonishing region of the sky with dozens of galaxies visible in a single field of view. Distant quasars become accessible, objects billions of light-years away whose light comes from material falling into supermassive black holes. Professional telescopes, 4 to 10 meters in aperture, reach magnitude 25 or fainter. In a single night of observation with a large telescope, a skilled observer can detect galaxies at redshifts above 1. meaning their light left them when the universe was less than half its current age, when the universe was denser and more active. The darkness almost entirely disappears at this depth. Every patch of sky contains objects. The Hubble Space Telescope, not limited by the Earth's atmosphere, reaches magnitude 31 in deep exposures. At this depth, essentially the entire sky is covered with galaxies. There is no truly empty patch. Every direction you look, there are galaxies as far back as Hubble can see, which is as far back as there were formed galaxies to see. And JWST, observing in the infrared at sensitivities inaccessible to Hubble, pushes even farther, seeing galaxies that existed when the universe was only a few 100 million years old. Objects at redshifts above 12. Objects whose light left them more than 13 billion years ago. Objects that have since evolved enormously. The early galactic structures JWST sees are the precursors of the mature galaxies we see nearby today. The darkness of the night sky is a function of the limit of your instrument. With every increase in sensitivity, the darkness recedes. More objects appear, the background level of light rises slightly, the richness of the universe becomes more apparent. But the darkness never entirely disappears. Even with the most sensitive instruments we have, there is a limit beyond which we cannot see. Not because nothing is there, but because of the recombination wall at 13.8 billion light-years, behind which the universe was opaque. And because of the accelerating expansion that is carrying distant objects beyond our event horizon. The darkness has structure, it has layers, it has a limit imposed by physics rather than by the sensitivity of our instruments. And the limit itself, the recombination wall, is luminous. It is the CMB. The darkness is bounded on all sides by this faint glow at 2.725 Kelvin, pervading all of space in all directions simultaneously. The darkness is not the end. It is the beginning of something else. The beginning of the regime where our optical windows close and our microwave windows open. Let us now talk about a specific astronomical phenomenon that illuminates one of the deepest connections between the darkness of the night sky and the large-scale structure of the universe, about galaxy voids and what they tell us. The large-scale structure of the universe, visible in galaxy surveys that map the positions of hundreds of thousands to millions of galaxies, is sometimes described as a cosmic web. Galaxies concentrate along filaments and at nodes where filaments intersect. Between the filaments and nodes are enormous, nearly empty regions called voids. These voids are among the largest structures in the universe. The Boötes void, discovered in 1981, is roughly 330 million light-years in diameter, an enormous region of space containing very few galaxies compared to the surrounding regions. The supervoid in Eridanus, sometimes called the cold spot, may be even larger. The voids are dark. Not dark in the sense of the empty patches between stars in our sky, but dark in the sense of a region of the universe with very low galaxy density. If you were inside a void, positioned at a random location within one, the night sky would contain fewer galaxies per unit angle, the cosmic web structure would be less visible, and the universe would look somewhat different. The voids are not truly empty. They contain diffuse gas. They contain dark matter in lower concentrations. They contain occasional dwarf galaxies. And they are pervaded by the same CMB as everywhere else. The voids are also not permanent features. They are growing. Matter flows outward from voids into the surrounding filaments, driven by the combined gravitational attraction of the denser filaments and nodes. Voids today are larger and emptier than voids were in the past. The existence of voids and the specific statistics of their size distribution is a powerful test of cosmological models. The size of the largest voids, the density of galaxies within them, the rate at which they grow, all of these depend on the balance between ordinary gravity, which pulls matter into filaments and nodes, and dark energy, which accelerates expansion and tends to prevent matter from clustering further on large scales. When cosmologists look at the darkness between galaxy clusters, at the cosmic voids, they are seeing a large-scale analogue of what Olbers was puzzling about when he looked at the darkness between individual stars. The darkness at cosmic scales has the same resolution as the darkness at stellar scales. The universe has a finite age and structure formed over that finite time, and not all of space has been filled with luminous objects. The distribution of galaxies and voids we see today is a snapshot of where structure formation has gotten in 13.8 billion years. Given more time, much more time, the structures would continue to evolve. But dark energy is putting a brake on further clustering, and the expansion is diluting the universe. The snapshot we see is where things are right now, in this specific epoch. Let us now talk about what the darkness of the night sky means for the search for extraterrestrial intelligence, about the Fermi paradox, and how the finite age of the universe connects to questions about other civilizations. In 1950, physicist Enrico Fermi famously asked at lunch with colleagues, "Where is everybody?" If intelligent civilizations arise throughout the galaxy with any reasonable frequency, and if any of them developed space travel or long-range communication over billions of years, we should expect signs of them to be detectable. The fact that we see no such signs, no alien radio transmissions, no Dyson spheres, no interstellar probes, no evidence of large-scale cosmic engineering, is itself a datum requiring explanation. The Fermi paradox is named for this observation, the silence of the universe in response to the expectation of abundance. The darkness of the night sky is a related but distinct observation. The night sky is dark because the universe is young, and the light from distant sources has not had time to fill it. But one might ask, should not an ancient civilization have been visible in some way, through its energy consumption, its large-scale structures, its communications? The connection is subtle but real. The universe is about 13.8 billion years old. The first stars formed about 100 to 200 million years after the Big Bang. Complex chemistry, the kind needed for life as we know it, required heavy elements produced in early stellar generations, which took billions of years to accumulate. The first roughly Earth-like planets in the right conditions probably formed somewhere around 8 to 9 billion years after the Big Bang. This means the window for technological civilizations is only a few billion years old at most. If it takes a billion years or more to develop a technological civilization after the planet forms, the universe has had only a few billion years to develop them. This is not enough time to fill the observable universe with evidence of civilizations, even if they are common. The universe is too young. The expansion of civilizations through space, even at modest fractions of the speed of light, would take millions to billions of years to cover cosmic distances. And civilizations that arose only billions of years ago have not had time to propagate their signals or their physical presence to us at our specific location. The darkness of the night sky and the silence of the Fermi paradox are both partly explained by the same thing. The universe is young. There has not been enough time. Not enough time for starlight from all sources to fill the sky. Not enough time for civilizations to have colonized the galaxy and made themselves unmistakably apparent. This does not mean we are alone. It means that even if intelligent life is common, we should not necessarily expect the evidence to be everywhere yet. The universe's youth, the same youth that makes the night sky dark, also limits the detectability of other civilizations. Every year of cosmic history adds a little more light to the night sky, and a little more time for civilizations to have developed and spread. We are at a specific moment in this process, early enough that the universe is still largely dark and still largely silent, if there is anything out there to hear. Let us now talk about something that brings this entire discussion back to the most personal scale, about what it means to be a conscious observer in this specific universe at this specific time. You exist. This is not obvious. It requires an enormous chain of specific events. The universe had to have a Big Bang with the specific parameters it did. If the expansion rate had been slightly different, galaxies would not have formed. If the fundamental constants had been slightly different, if gravity was stronger or weaker, if the electromagnetic force were different, stars would not have burned with the right properties to produce the heavy elements needed for your chemistry. The first stars had to form and die, producing carbon, oxygen, nitrogen, calcium, iron, and the other elements of your body. This took billions of years. The galaxy that formed from the enriched gas had to be the right kind, a large spiral, stable enough over billions of years to allow solar systems to persist, but not so active that gamma-ray bursts or supernova explosions sterilized the developing biosphere. A specific molecular cloud in this galaxy had to collapse to form a G-type main-sequence star, our Sun, stable enough to burn steadily for billions of years. The specific impact history of the forming solar system had to produce, at the right distance from this star, a rocky planet with the right mass, the right amount of water, and the right kind of geological activity to maintain a habitable climate over billions of years. Life had to arise on this planet, a process we do not understand in its details, and then had to evolve over billions of years through an enormously complex sequence of evolutionary history that led, eventually and contingently, to beings capable of asking the question, why is the sky dark? This chain, from Big Bang to question, is the sequence of events that produces the situation we are in. At every step, the chain could have gone differently, and the question would never have been asked. The darkness of the night sky and the universe's history that it encodes is what made this chain possible. The specific age of the universe, the specific expansion rate, the specific character of dark energy, all of these are what allowed enough time for enough complexity to develop for the question to be asked. The question and the asker are both products of the same universe. The darkness of the sky is evidence of the history that produced the being that notices the darkness. This is not mystical, it is physical. The universe is 13.8 billion years old. The sky is dark because of this age. The being that notices the dark sky is about 13.8 billion years in the making, from Big Bang to you, through stars and supernovae and planets and evolution. The darkness and the noticer share the same origin. When you look at the dark sky, you are the universe noticing itself. The same physical processes that produce the darkness, the finite age, the expansion, the evolution of structure, produced you. The darkness and your awareness of the darkness are two outputs of the same 13.8 billion year process. This is one of the most remarkable facts about the universe, that it should produce beings who notice it and wonder about it. That the same physical laws that govern the expansion of space and the burning of stars also produce, in the right circumstances, organisms with nervous systems capable of measuring redshifts and detecting the CMB and asking why the sky is dark. Let us now talk about the specific experience you can have tonight, about what to do with all of this understanding when you are actually standing under the night sky. Go outside. Choose a clear night. Get away from artificial light if you can. Give your eyes 20 to 30 minutes to fully dark adapt. First, just look. Take in the scene without analysis. The stars, the Milky Way if visible, the black between. Let the scale settle on you. Not intellectually, but experientially. The sky you are looking at extends in every direction. You are inside it, a point in it. Not above it looking down, inside it looking out. Then look at a specific star. Not the name, not the catalogue designation, just the light. That light is real. It left a real object at a specific moment in the past. In some cases years ago, in some cases hundreds of years ago, in some cases thousands. The star may have changed since then. It is emitting that light right now, or rather it was by the time the light gets to you. Then look at the darkness beside that star, not at the star, beside it. The darkness there is not empty. There are galaxies in that direction, millions of light years away, receding from us, carrying ancient light that has been travelling since before Earth existed. Your eye cannot collect enough photons from them to register them, but they are there. Think about the CMB. Right now, at this moment, photons of the CMB are arriving from every direction simultaneously. From the direction of the star you were just looking at, from the direction of the darkness beside it, from the direction of the zenith and the horizon and every compass point simultaneously. The universe's first light, stretched by 13 billion years of expansion to microwave wavelengths, arriving everywhere all the time, carrying the pattern of the density fluctuations that seeded all the structure you can see. You are bathed in it. You cannot feel it. Your eyes cannot detect it, but it is real. And look at the darkness one more time with all of this in mind. That darkness is 13.8 billion light years deep. It is not the absence of universe. It is the presence of a universe too young, too fast expanding to have filled it with visible light yet. It is the universe's way of showing you its age, of demonstrating that it had a beginning, of pointing with the eloquence of pure physical fact to the Big Bang. No telescope required, no mathematics required, just eyes and patience and the willingness to take the darkness seriously. The universe is telling you its history. You can read it in the darkness between the stars, not metaphorically, physically. The darkness encodes the finite age. The finite age implies the Big Bang. The Big Bang is confirmed by the CMB. The CMB fluctuations reveal the parameters of cosmology. And all of this is present, in principle, in the information content of the night sky for any observer patient enough to read it. The stars and galaxies are the bright text. The darkness is the context that makes the text readable, the white space without which the letters have no meaning. Both are necessary, both are real, both are saying the same thing. The universe began, and you are here because it did. Go outside tonight. Find the darkest place you can, away from streetlights, away from windows. Let your eyes adapt. 20 minutes, 30 if you can manage it. Let the pupils open. Let the rods in your retina recover their full sensitivity. Then look up. The stars are there, thousands of them if the sky is dark enough. The Milky Way, if you are far enough from the city, a band of hundreds of millions of stars merged into something you can almost touch. Planets moving slowly against the fixed stars. If you know where to look, a faint smudge in Andromeda. Light that left another galaxy 2.5 million years ago, arriving at your eye tonight. And between all of it, darkness. That darkness is what tonight has been about, not the stars, the darkness between them. It seems like nothing. It seems like absence, like the universe simply ran out of things to put there. It is not nothing. Every dark point between the stars is a direction in space that extends 13.8 billion light years to the boundary of what we can observe. Behind that boundary, more universe, possibly infinitely more. But their light is still in transit, still traveling toward us through expanding space, still crossing distances that grow larger as the photons travel them. The light has not arrived yet. The sky is dark because it has not arrived yet. This is the resolution of a paradox that troubled astronomers for centuries. Heinrich Olbers stated it clearly in 1823, but it had been noticed before by Kepler in 1610, who used it as an argument against infinite space. By Edmund Halley. By others who noticed that a universe full of stars should produce a sky full of light, but somehow did not. Edgar Allan Poe, a poet, not a scientist, understood the answer intuitively in 1848. He wrote that the darkness of the night sky was explained by the finite age of the universe, that light from infinitely distant stars simply had not had time to reach us. He was right. He wrote it as poetry. The science came later. The science came from Edwin Hubble in 1929, measuring the spectra of galaxies, finding that the farther a galaxy, the faster it recedes. The universe is expanding. If it is expanding now, it was smaller in the past, smaller and denser and hotter. Continue backward far enough, everything was in the same place. Everything was the same thing, the Big Bang. 13.8 billion years ago, not an explosion in space, the beginning of space, the beginning of time. The beginning of the physical laws that govern everything you have ever seen or touched or thought about. Everything came from that moment. Every atom in your body was forged in stars born from the material of that moment. The carbon in your cells, the oxygen in your lungs, the iron in your blood. All of it produced in the nuclear furnaces of stars that lived and died before the sun existed, and scattered across space in supernovae, and gathered again into a new solar system, and eventually into you. You are 13.8 billion years old, made from the universe, standing inside it, looking at it. And it is dark. It is dark because it is young, because 13.8 billion years is not infinity, because light travels fast but not instantaneously, because there has not been enough time for the light from all the universe's stars to fill every corner of the sky. And also because the universe is expanding. Because every photon from a distant galaxy is stretched by the expansion of space, its energy reduced, its wavelength lengthened, shifted from visible light into infrared, into microwave, into wavelengths your eyes cannot detect. The sky is dark in visible light because much of the universe's light has been redshifted beyond your ability to see it. What remains, arriving from every direction simultaneously, invisible to your eyes but real and measurable, is the cosmic microwave background. The light from 380,000 years after the Big Bang, stretched by 13.8 billion years of expansion into microwaves at 2.725 Kelvin, almost absolute zero, the faintest possible glow, the universe's oldest light. It is hitting you right now, every second, from every direction. The afterglow of the Big Bang, pervading all of space, surrounding you completely, carrying the pattern of the density fluctuations that seeded every galaxy and star and planet and you. You cannot feel it. Your eyes cannot see it, but it is there. The darkness is not empty. The darkness is full of history, full of photons still in transit from galaxies too far away and too faint for your eyes to catch, full of CMB photons carrying the echo of the beginning, full of dark matter streaming through you at this moment, invisible and undetected, but comprising 27% of everything the universe contains. Full of dark energy, the mysterious, repulsive force that is accelerating the expansion, that will eventually carry most of the universe beyond our observable horizon, that is slowly making our observable sky smaller. You are standing inside all of this. And the sky is dark. It is dark because the universe had a beginning, because it is not infinitely old, because light has had only finite time to travel, because space is expanding and stretching that light toward invisibility. The darkness is a signature, a proof. A physical demonstration visible to any naked eye on any clear night throughout all of human history that the universe is not eternal, that it began, that we live in its specific youth, old enough for stars and planets and life, young enough that the darkness still dominates the spaces between. A child's question, the universe's deepest answer. Go outside. Find the darkness between the stars. It has been waiting for you to notice it. It has been telling you the history of everything. All you had to do was look.